So welcome to the HL topic in this unit, rate expression and reaction mechanisms. So I'm going to link rate expressions to the mechanisms of reactions. So by the end of the unit, you should know that reactions may occur by more than one step, and the slowest step is the rate determining step, also known as the RDS, or simplified to RDS. That the molecularity of an elementary step is the number of reactant particles taking part in that step. The order of a reaction can either be an integer or a fractional. Okay, so what the order of a reaction is, something we'll explore. Rate equations can only be determined experimentally, and the value of the rate constant, lowercase k, is affected by temperature, and its units determined by the overall order of the reaction. And catalysts can alter the reaction mechanism, introducing a step with lower activation energy, which will determine the rate determining step. By the end of the unit, you should be able to deduce the rate expression for an equation from experimental data and solving problems involving rate expression. Sketch, identify, and analyze graphical representations for zero, first, and second order reactions, and evaluate a proposed reaction mechanism to be consistent with both kinetic and stoichiometric data. So mass revision there, so 1 to the negative x is 1 over x. Am times a to the n is going to be am to the n, so you're basically adding the powers. There we go, there's an example there. And basically, if you're dividing powers, you basically are subtracting. Okay. So the rate equation. So this links the rate of the reaction to the concentration of the reactant. So we've kind of already slightly looked at it earlier. It can only be found by doing experiments. Okay, it can only be found experimentally. It cannot be found just by looking at an equation. So the chemical equation here, we have A plus B giving C plus D. A proposed rate equation is R, the rate, equals K, which is the rate constant, times the concentration of A times the concentration of B squared. Okay, so by saying that, if A is doubled, then the rate doubles. If the concentration of B doubles, then the rate equation there quadruples, because 2 times 2 is 4. That's not right, 2 squared is 4. 2 squared is 4. Okay, so R is the rate of the reaction. In this particular case, it's moles, decimeters cubed, seconds to the minus 1, and K is the rate constant. Okay, and that unit depends on the rate equation. Okay, so the rate of reaction is simply the concentration changing over time of either the reactants or the products, and the rate constant depends on the rate equation. Catalysts can speed up reactions, so they also need to be included in rate equations. So in terms of the order of a reaction, it's basically in 2 parts. The individual order is the power to which the concentration is raised in the rate equation. Okay, so if you see A to the power, just A like that, concentration of A, it's actually the concentration to the raised to the power of 1, but we don't really put 1 in the equation. Okay, and the overall order is the sum of the individual orders in a rate equation. So the example provided here, we have a rate equation, R equals K, concentration of A, multiplied by the concentration of B squared. So the order of, with respect to A is 1. Okay, so as I said, A to the power of 1 for all intents and purposes is just the concentration of A, and means it's first order in A, and order with respect to B is 2. It is second order because the superscript is 2 here. Okay, and the sum therefore is going to be this order on A plus the order of 2, which will be the overall order of the reaction, 3. A value is 0 if the rate is unaffected by how much the substance is present. Okay, so as mentioned earlier, the units of the rate constant are dependent on the overall order of the reaction. Okay, so if you divide the rate by as many concentrations in moles per decimeters cubed as appear in the rate equation, you get the rate constant. Okay, so the overall order of a reaction is 0. Then the units are moles per decimeters cubed per second. Okay, if the overall order is 1, it's reciprocal seconds. If the overall order is 2, it's per mole, decimeters cubed per second. And if the overall order is 3, then it's moles to the minus 2 decimeters to the power of 6 per second. Okay, so just to illustrate that point, if R is going to be equal to the K times concentration of A, then the rate constant K will have units of seconds to the minus 1, okay, because it's going to be basically first order, okay, when we won't show that one. If R is K, the concentration of A squared, then it's going to be second order, so the units are moles to the minus 1, decimeters cubed, seconds to the minus 1. Notice the order is not necessarily most important, okay, in this particular example. As long as you get the correct units, the order of the units isn't critical. And if R is K times concentration of A times concentration of B, it's going to be third order, because obviously it's going to be 1 plus 2, which will equal 3, so third order overall, so it's going to have the corresponding units of K of moles to the minus 2, decimeters to the power of 6, seconds to the minus 1. So as previously discussed, the only way you can determine the rate constant at particular points is by graphically determining it through experiment. Okay, so the variation in rate can be investigated by measuring the change in concentration of one of the reactants or products, plotting a graph, and then finding the gradients at the curve at different concentrations, essentially at the tangent. So here's a reaction in solution. A reacts with B to form C plus D, and the concentration was measured by the experimenter for B every 200 minutes. You can see it's quite a slow reaction. To calculate the rate, which we'll look at in the next slide in further detail, the rate of reaction at any moment can be found by the gradient of the tangent at that point. The steeper the gradient, the faster the rate of reaction. If you place a rule on the outside of the curve and draw a line as shown on the graph, which we'll show in the next slide, you can work out the rate. So with this particular example here, we're trying to work out the rate of reaction at 1.2 moles per centimeters cubed. So the gradient will be the change in y over change in x. So we've been given negative 1.6 divided by 1520, okay? And the rate is negative 1.05 times 10 to the 3 moles per decimeter cubed. The reason why the rate is negative is because the reaction is, of course, slowing down. And also it's negative because the reactant is B, okay? So we're losing B to form C and D. So we can use this information to try and experimentally determine the order of a reaction. So if you have a theory of what an order of a reaction could be, by doing the experiment, you can then kind of use the experimental data you've got from the graph to support your theory behind what you think the order of a reaction is. So the order of a reaction can be found by measuring the rate at different times during a reaction and plotting the rate against either concentration or time. The shape of the curve provides an indication of the order. Okay, so if you plot concentration against time for a reactant, it would be 0 order if it would be a straight line. It is first order if it's slightly sloping, and second order if the curve declines steeply at first, then levels out. Okay, remembering this is finding the order of one of the reactants. Okay, you'd have to do it for the other reactants to then determine, or other reactants to determine the overall order of the reaction. So if you plot the rate of reaction versus concentration instead, it would be 0 order if there is just flat line, okay, there's no relationship between the concentration and the rate of reaction. It would be first order if the rate is proportional to the concentration, so you get a straight line with a fixed gradient, and second order if the rate is proportional to the square of the concentration, which makes sense when you think about it. Okay, so in terms of graphical determination, there's some questions there for you. Calculate the rate of reaction at 1, 0.75, 0.5, and 0.25 moles per centimeter cubed, and plot a graph of V versus concentration of A. Calculate the time it takes for concentration A to go from 1 to 0.5 moles per centimeter cubed and 0.5 to 0.25 moles per centimeter cubed, and deduce from the graph that the order with respect to A is 1, and calculate the value and units of the rate constant. So we'll be doing this actual task in class. Okay, so the experimental determination of order, there's two methods. There's the plotting of a graph, which we've looked at. Okay, so basically either plotting the concentration time graph or plotting another graph of rate against concentration at that point. If it gives a straight line, the rate must be directly proportional to concentration, first order. If the plot is a curve, then it must be of another order. And if a straight line would mean second order, this method is based on, so basically a plot of the curve, then I must have another order. Try plotting the rate versus concentration squared this time. If that's a straight line, then it means it must be second order. And essentially this is based on trial and method. As you can see, my masters is really fun. The second method is doing initial rates method, which is doing a series of experiments at the same temperature, keeping temperature constant, at different concentrations of a reactant, but keeping all other things constant. Then plot a series of concentration time graphs and calculate the initial rates, which are the slopes of the curve at the start, for each of the reactions, and from the results calculate a relationship between concentration and rate, and hence you can then deduce the rate equation. To find others, order directly, logarithmic plots are required. So that gets a bit more complicated. So in an experiment between A and B, the initial rates of reaction were found for various starting concentrations of A and B. Okay, and that's placed in the table there. So what I want you to do is work out the individual orders for A and B, the overall order of the reaction, the rate equation, the value of the rate constant K, and the units of the rate constant. Okay, so you need to work that out for yourself, and then we're going to work out the answers in the next slide. So pause the video now, and then once you've done all your analysis, come back and see if you got it correct. Right, so the individual orders for A and B are thus far. So experiment 1, the order for a concentration of A is 0.5, concentration of B is then 1, initial rate is 2. Concentration of A is 1.5 in the second experiment, concentration of B is 1, so therefore the initial rate is 6. And finally, in experiment 3, the concentration of A is 0.5, the concentration of B is 2, the initial rate therefore is 8. So when B was kept constant, okay, which is experiments 1 and 2, the concentration of A tripled. The rate also triples from 2 to 6. Therefore, the rate is proportional to the concentration of A. So the order of the reaction with respect to A is 1. Okay. So when the concentration of A is kept constant, which is experiments 1 and 3, B is doubled. The rate equation, the rate quadruples 2 to 8. Therefore, the rate is proportional to concentration of B squared. The order of reaction with respect to B is 2. B, and finally, the overall reaction is the sum of the two orders. So it's going to be 1 plus 2, which equals 3. So in terms of the rate equation, by combining the two proportionality relationships, you can construct the overall rate equation. The rate is going to be K, concentration of A times concentration of B squared. The value of the rate constant at K will be equal to the rate divided by the concentration of A times concentration of B squared. So 8 divided by 0.5 times 0.2 squared, which will be 4. The units of the rate constant are going to be dividing the rate, which is moles decimeters cubed seconds to the minus 1, by 3 times the concentration, moles per decimeters cubed. Do the fancy algebra, and you get decimeters to the power of 6, moles to the minus 1, seconds to the minus 1. So it's third order. Therefore, K is 4 decimeters to the 6, moles to the minus 2, seconds to the minus 1. So this is all linked to reaction mechanisms and ways that we can try and determine reaction mechanisms for reactions. Okay, so reactions may occur all at once or through several discrete small steps. In a multi-step process, one of the steps will be slower than all the others. We call this step the rate determining step. The order of the reaction for this step will be the same as the order of reaction for the entire reaction. Okay, so if you look at the examples here, the cars are slowed at plaza A, okay, then that's going to determine the rate of reaction, or the rate of how fast the cars go. If the cars are slowed at plaza B, then the overall reaction will be determined by the rate of slowing at plaza B. So slow initial steps. So here's a reaction, nitrous dioxide plus carbon monoxide giving nitrous oxide plus carbon dioxide. The rate law for this reaction is found experimentally to be KNO2 squared, concentration of NO2 squared, and carbon monoxide is necessary for this reaction to occur, but the rate of reaction does not depend on its concentration. This suggests the reaction occurs in 2 steps, okay, with one being the rate determining step. Okay, so the proposed mechanism for this reaction is that in the first step, nitrogen dioxide plus nitrogen dioxide gives nitrogen trioxide plus nitrogen oxide, which is a slow reaction. And step 2, nitrogen trioxide plus carbon monoxide gives nitrogen dioxide plus carbon dioxide, which is fast, which makes sense because if that was the case, then carbon dioxide wouldn't be in the rate equation. The nitrogen trioxide intermediate is consumed in the second step, and as carbon monoxide is not involved in the slow rate determining step, it does not appear in the rate law. Okay, so in this particular case, the cars are slowed at plaza A, not plaza B. Okay, so basically the overall rate of reaction is determined by the slowing of the cars at plaza A. So in terms of the molecules of the reaction mechanism, unimolecular steps involve a single species as reactant, whereas bimolecular steps involve collisions of 2 species that form a transition state or an activated complex that cannot be isolated. So there's the 2 ways that it can happen. So the difference between intermediate and transition states, which will become more important when we look at organic chemistry, is that intermediates exist for a finite time, whereas transition states only exist for a very, very small amount of time. They occur at a potential energy minimum for intermediates, whereas transition states occur at a potential energy maximum. Intermediates are formed in one step of a reaction and consumed in the subsequent step, just like the nitrogen trioxide, and transition states exist partway through every step of a reaction. So if we look at the energy reaction progress diagram, which will become more important as we look at organic chemistry, you can see the differences between intermediates and transition states. Okay, so you can see here that the intermediate states here are at energy minima, okay, and these guys, transition states, are going to be at energy maxima. Okay, so those are the main differences you can see, and transition states are transient, whereas basically the intermediate states exist in both of the steps, whereas transition states only exist in one step because it's unimolecular. So you can determine the order of a reaction from a reaction mechanism, or you can justify a reaction mechanism from the experimental determination of an order of a reaction. So for the following, assume a bimolecular reaction, A plus B going to C plus D. So use the rate limiting step in the reaction mechanism to determine the reaction order of the reaction in the preceding slides. Okay, the nitrogen dioxide example. Okay, so the mechanism in the nitrogen dioxide example is A plus B goes to X plus C, which is your slow rate determining step, and then A reacts with X, this intermediate, to form D, the product. Okay, so essentially the overall reaction is 2A plus B gives C plus D overall. Okay, so the rate expression for the rate determining step is going to be first order in A and first order in B. So K equals the concentration of A times the concentration of B. The order is second order. So in terms of a mechanism, which is possible also, is that A plus B is in equilibrium with X, which is fast. A plus X, A then reacts with X to form C plus D, which is the slow rate determining step. Okay, so those are your possibilities. So again, the overall reaction would be the same, but now it's the second step that's the rate determining step. So if we do the rate expression this time, you'll see that it's going to be equaling R equals K, concentration of A times the concentration of X, because now X is in the rate determining step, and remembering that the concentration of X will essentially be the concentration of A times the concentration of B. So that means that now the rate determining step, the rate expression with concentration of K, not concentration of K, sorry, the rate equation times concentration of A all squared times B. So it's now gone from being a second order reaction when the first step was the rate determining step to a third order reaction when the second step is the rate determining step, because X does not exist in the initial reaction as a reactant. So another possibility is that A plus A gives A squared, which is a slow rate determining step, and A squared plus B then goes to C plus D. So there's actually no intermediate per se. In that particular example, you have rate expression of K equals A squared. So it's again second order. So that would be consistent. But this time it's second order only in A. B has no effect. Another possibility is that B goes to X, and this is a slow rate determining step. And then X plus A, this intermediate goes to Y plus C, a second intermediate, which is fast. And the second intermediate then interacts with A to form D, which is fast. So in this particular case, the order is 1 because only the B is in the constant, is the only molecule involved in the rate determining step in terms of a reactant. Or you can have A reacting with A to form A squared, which is the fast step, and then this bimolecular A forming with B to form C plus D, which is a slow rate determining step. This will also become third order because B must exist in the initial reaction, okay, which is your rate determining step. So in terms of guessing the rate determining step, determine a possible mechanism, see which fits the rate equation. So for example, the A plus B plus C gives an ABC rate. What is the mechanism in RDS, or the rate determining step? Well, the chances of three substances all hitting it in the right place at the same time is unlikely. So the options are A plus B gives AB, and then AB plus C gives ABC, or A plus C gives AC, and then AC plus B gives ABC, or B plus C gives BC, and then BC plus A gives ABC. As C is zero order and the rate is first order, A and B, situation 1 seems more likely, with the first reaction being the rate determining step. Okay, so here's a final problem. Okay, so we have a problem here. So 2N2O plus goes to make nitrogen plus oxygen, and the rate is given as a rate constant times the concentration of N2O all squared. What is the rate determining step? So here's the answer. So 2N2O plus N2 plus O2, the rate agrees, or N2O plus nitrogen and this oxygen atom, if the rate determining step, then the rate disagrees here. Okay, that means that N2O plus oxygen atom gives nitrogen plus oxygen, so it must be in the rate determining step. So the rate must be concentration of N2O times concentration of O, which equals concentration of N2O plus N2O, which gives concentration of N2O all squared, so the rate agrees too. So that must be the rate determining step. And that is pretty much all we need to know for rate equations.